So we've seen that if a matrix has n distinct eigenvalues, then it is diagonalizable. At the same time, the converse is not true. Observe along with this that so A is diagonalizable if and only if, right, if and only if the algebraic multiplicity of the eigenvalue is equal to the geometric multiplicity of the eigenvalue for every eigenvalue, right? For every lambda in sigma A. Sigma A represents the collection of all eigenvalues of A. Right? This is also easy to note. Right? Why is this the case? Because we've seen that A is diagonalizable if and only if there exists n linearly independent eigenvectors. Eigenvectors of A. Right? Right. Observe that so if you want n linearly independent eigenvectors, right? So for every corresponding lambda there should be a linearly independent eigenvector, right? Where lambda can repeat. Okay. So if there is a say an eigenvalue 2, right, which has arithmetic multiplicity 2, then that corresponding to that eigenvalue 2, you should have two eigenvectors, right? Only then only then A will be diagonalizable. Okay. So another condition is that okay, so an equivalent condition is that so if A is in MNR, okay, so provided A is in MNR, we say that there exists a basis. So you can say there exists a basis, okay, whose vectors or whose elements, okay, whose elements or vectors are eigenvectors of A. So this is same as the previous statement, right? So if you have n linearly independent eigenvectors, that means you can have a basis, right? Basis of what? That can be Rn or Cn, right? Depends. The next important result. So let me just write down. Result is that if A is diagonalizable, then A square is also diagonalizable. Or sorry, I would say A inverse. The inverse is also diagonalizable. Why do I say this? See, if A is diagonalizable, what does that mean? That means you can write A as P inverse AP for some invertible matrix P. Sorry, I'm so sorry. You can write it as P inverse DP, right? Where D is a diagonal matrix. Right? Then what can you say about A inverse? Right? A inverse would be equal to this would be P inverse, right? And then you have D inverse, and then you have P, right? So again, you're able to, since the inverse of D is also a diagonal matrix, in fact, it is nothing but 1 by dii, whatever. So what we are observing is that the inverse can also be written as P inverse into some diagonal matrix times P, right? Let's look at another result. So this is a question, right? Suppose A square is diagonalizable. then is A diagonalizable? That is a question. So whenever you have such questions like true or false kind of, look at simple and extreme examples. Right? So what is the simplest example of a diagonalizable matrix? The zero matrix, right? So let's make A such that, right? Construct an A such that A square is this. Right? Construct a non-diagonal or non-diagonalizable set A, right? And we've seen that to construct what do you say, non-diagonal what do you say, non-diagonalizable, matrices, all you need to do is so we know that nilpotent matrices are not diagonalizable because the only eigenvalue they have is 0. Okay? So let's take A to be 0, 1, 0, 0. Right? Then A square will be this. And this is not diagonalizable, right? A is diagonalizable. Why is it not diagonalizable? Suppose you can write A as A equals to P inverse into some D, right? Some D into P inverse into P, right? But this D has to be the zero matrix. That means A has to be the zero matrix, which is a contradiction. So this is the contradiction. Okay. Now what about so let's look at another example, right? Suppose A comma B are diagonalizable, right? Matrices, right? So number 8, okay? Number 8 says that A plus B is diagonalizable. Option B says that AB is diagonalizable. So which of them are true? So if you have two diagonalizable matrices, right, the sum may or may not be diagonalizable, right? Because what do you do in sum actually? So how do you construct a non-diagonalizable matrix? So we've seen earlier that strictly upper triangular matrices like this form matrices, right? This is strictly upper triangular. This so whenever you have strictly upper triangular matrices with the same diagonal entries, this is a candidate for A plus B. So you need to design A and B such that this is right. This is non-diagonalizable. So that means we can discard option A, right? But for that we need to find diagonal matrices A and B, right? If you look at this matrix, so let's take A to be 1, 0, 0, and say half. Okay. And B is 0, half, 0, 1. This is okay, right? So this in itself is diagonalizable. Why is that the case? Because of distinct eigenvalues, right? So distinct eigenvalues, or sorry, distinct eigenvalues. That means linearly independent eigenvalues. So same case here, right? But observe that this is not diagonalizable. So the product is diagonal. This is false statement, right? Need not be. need not be. That's done. The next one says AB is diagonalizable. Just think about so let me try to prove this. So A can be written as P inverse AP, right? B can be written as Q inverse BQ, right? So what does this mean? This means that AB can be written as, right? AB can be written as P inverse A, PQ inverse BP, right? I think again it will not be diagonalizable. We'll use the same tactic. Right? We'll construct A and B such that A plus B ends up like this. And we want to create A and B so that uh, the diagonal elements are distinct. Okay. I'm just confused what to put in here. Let's see what makes sense. Okay, I'm so sorry. This should be AB. Right. And in B, let's take, yeah, same thing. Again, I'm confused what to put in here. Let's see. Okay. Uh, this has to be 1, so minus 1 times something. Let's take, say for example, let's take a 0 here and let's take a 1 here, right? So just observe that this holds. AB will be, yeah, fine, this is it. What do we have in this case? This is not diagonalizable, right? This one. But individually, these are diagonalizable. This is diagonalizable. This is also diagonalizable. It's so, okay, this is fine. So again, this is also false. Need not be. This is done. From this example, we can also conclude that, see, that invertible need not imply so. So the question is, if A is invertible, then A is diagonalizable. Is this true or false? That is the question. And it's actually false, right? Because take A to be, right? Then what will be the inverse? Inverse will exist, right? This is invertible, but this is not diagonalizable. So let's look at few, properties of eigenvalues. Right. So the first one I would like to say is that Suppose, for example, you take a, okay, so see, first of all, if you have an upper triangular matrix or a lower triangular matrix, right, then the eigenvalues are precisely the diagonal entries. So this is one. So we know that if you take the sum of all eigenvalues, you get the trace. If you take the product, get the determinant. Now let's see that if suppose you have a matrix A, right? So you have a matrix A where you can say the sum of elements of each row is, say, some lambda. Suppose, for example,